Okay, so this is the Python version for question 10 of chapter 3 of an introduction to statistical learning. I've already made a video for the R code, and this is the Python code. So you can see the R version if that's what you're looking for instead. Okay, in this question, we are going to be using a different data set from the ISLP library. It's called Carseats, and we're going to fit regression to it, and then do some thinking and some different analyses of our regression. So we'll go through those piecemeal instead of reading everything all at once. Before you start, you need to make sure you've installed and imported the ISLP library as well as these other libraries. Okay, and I've already done that. So we need to load the Carseats data set, and so I'm doing that here. And then I'm going to look at Carseats a little bit, and we are going to be interested in just a few variables: sales, price, urban, and US. And so let's glean some things here. So sales looks to be how many sales are taking place at different stores. Oh, I should say I did some background reading here. And sales is, so this whole data set is car seat sales across 400 different stores. And so this is the number of sales in thousands of units. The other one is price, so the price of these car seats. And urban and US are factors, or I guess that's really our language, but they are categorical variables, where the store is either located in an urban setting or not, and it's located in the US or not. Okay. So part B, or I'm sorry, part A, we want to fit a regression to sales over price, urban, and US. And so we'll get into that. So first we need to make sure that all of our variables are in the right format. So we need to make sure that price is a numeric, okay, and we need to make sure that urban and US are categorical variables. Okay, and then I'm going to create my X, my design matrix. This is what I'm going to regress on. What am I regressing? I'm regressing Y, which is car seat sales. Okay, and then to my X matrix here that I've created, I need to add a constant so that the model will also estimate the intercept. And I create my model right here, and that's all it's asking us to do. Okay, so I've ran that. Now it asks us to provide an interpretation of each coefficient in the model. Okay, so I'm going to use the summary function here, and print it. I get this nice printout. And so what I'm interested here for this question is right here in this table. Okay. Okay. What can we learn from this? So one thing that we can learn is that the significant associations with sales happen to be price, and we can see that because of the very low p-value, and US, which is here, and that urban does not seem to have a significant p-value. So the association does not seem to be significant between urban and sales. Notice here that in the variable names or the coefficient names, that Python has gone through and added yes. Okay, it's because these are categorical variables. There's two categories, yes and no. And so when we run the regression, we need to binarize, if that's a word, or get dummies, right? That's what we're doing here, right? Where we encode urban and US as 1 and 0, okay? And so urban has been encoded as 1 and 0, and yes is 1, and so that's what it's telling us there. Okay, and so we've seen the two significant associations, and it seems then that our best estimate for how price is affecting sales is that as price goes up in 1 unit, sales decrease by 0.5 units. Okay, and so a unit is 1,000 car seats, so it's 50 car seats for every, I'm guessing $1, but it doesn't specify. So that seems pretty steep to me. So a unit of price might be more than $1. And similarly, a store in the US, all else being equal, is predicted to sell 1.2 more units than a store outside of the US. And 1.2 times 1,000 car seats is 1,200 more car seats. Okay. Part C wants us to write out the equation for our regression. Okay, and so I've done that here, and you can look at it. But the generic regression again is just the alpha plus the beta price times price, beta urban times urban, beta US times US, and then we can just use the values that we've already that we've estimated, and we can just plug those into the regression there. Okay. It wants us to take care to make sure that we are paying attention to the fact that both urban and US are categorical variables, and they are encoded as 1 and 0, right? And so I could put this as a 1 and this is a 1. I couldn't, but I'm not really sure how they want us to take care of this, but I'm just saying that urban, yes. So when urban is yes, then this is all that. Okay, and the value when it's no is 0. Okay. Okay. Now the next part D, wants us to look back at the coefficients and figure out for which of these coefficients here can we reject the null hypothesis. Well, we've already kind of discussed that. We can reject the null hypothesis for price and for US because these p-values are very low, and for urban. We should not reject the null hypothesis. Okay. Part E then wants us to take the compelling variables from the first regression and make a second regression using only the compelling variables. Okay. So here I'm making another design matrix, but I'm only using price and US okay, sorry, I had a little glitch. Anyway, so we need to get different data, or just a subset of the data. Okay, again, add a constant to it so I can estimate the intercept, and then I am going to run a new regression that I'm calling CS reg trunk for truncated. Okay, so I run this guy, and part F wants us to determine how well the models fit the data. Okay, and so the one way that we can do that is I can look at the summaries from both of these functions. Okay, so this top summary right here, I think probably ends right here. This is for the first regression, and then the bottom part is for the truncated regression. Okay. And so with this data right here, we can look at some things that help inform us about the fit of these models. So I've taken those important ones, or some of those important ones, and put them in this table. So the first one is multiple R squared, or just R squared for multiple regression. Okay, and so that's up here. Okay, and so here's the value for the two, and we notice that these are equivalent between the two models. And so which model is better? Well, right now we're saying that it's a draw, but I'm going to come back to that. We also have adjusted R squared. Okay, here's adjusted R squared. And we see that the second model has a slightly higher adjusted R squared. What is adjusted R squared? Okay, now recall that R squared is a assessment of the fit of the model, and it's roughly, it's summarizing how much of the variance in the data does the model account for, basically. And so the higher the R squared value, the better, or the better it fits, I should say. But now remember that as we make a model more complex by adding more explanatory terms, we will tend to fit the data better generally, but we are risking overfitting. And so one of the ways that we can take care of that is we can account for the number of explanatory variables are in our model. And that's what adjusted R squared is. It's like R squared, but it is accounting for the number of parameters that we have used to fit the data, right? And so here we see that the second model is slightly better than the first. I mean, marginally better. But taking what we just learned about adjusted R squared, if we go back to multiple R squared, we know that the second regression is simpler. It has fewer terms than the first one, and yet they have equal R squared values. And so already we should probably lean towards the second model as fitting the data better. Okay, so even though I put draw here, even from here, if we knew a little bit about the models, we might conclude that the second model is better. Okay, and then the last one here is the F statistic and its associated p-value, right, which is here and here. Okay, so these are the two values. The higher the p-value, the better, roughly, the better the model is doing in fitting the data. And we see that the second model is doing better. Okay. Part G, we want to get confidence intervals for our coefficients. Okay, and so I can do that with the conf underscore int at a confidence level of 0.5. Okay, so these would be 95% confidence intervals. Okay, so the alpha is 1 minus 0.95. So here's the confidence intervals for our different variables. Now, one thing to point out here is that recall that the p-values for our coefficients were both significant. They were both below 0.5. Okay. Well, the fact that they are significant is also reflected here. Okay. So to a confidence level of alpha equals 0.05, notice that these confidence intervals do not cross 0. This is both of these are on negative values and both of these are positive values. Okay, so that means that this corresponds to p-values that are less than 0.05. Okay, okay, and now lastly for part H, where are we at here? For part H, we want to look for outliers and high leverage points in the data set according to our models. Okay, so I'm going to, this is the code, but I'm just going to plot this and talk about it a little bit. So the first we have a plot here. And so the y-axis is leverage, and the x-axis is residuals or normalized residuals. So what is a high leverage point? Well, a high leverage point in the graph is a value that's way up on the y-axis here. And a high leverage point is a point that could potentially exert a lot of influence over the fit of the linear regression model. Okay, but that does not necessarily mean that it is an outlier. Okay, and it also does not mean that it is having undue influence over the fit of the regression. For it to have undue fit over the regression, it will typically also have a large residual, and so it would be more in this region of the plot, right? Which it is not. So even though there is at least one high leverage point and maybe a few, if you looked at these, it's not clear that any of them are really having undue influence in terms of being outliers. Okay, that's it.